Hello everyone, my name is Edmon Begoli and I greet you from rainy and muggy Knoxville in my Grizzly Adams pandemic edition with the obligatory picture on the wall to make my setting better. I found some pictures my mother gave me from central France depicting some quaint store in the village that I've never been to, and so there it is. It decorates my wall and makes it look less boring. Um, Otherwise, I'm a graphic computer scientist from Oak Ridge National Lab, leading several large and I would say important initiatives because they touch on human lives and fulfill an important mission. And um, in terms of this summit and relationship with our Berkeley team from Rise Lab and now Anyscale, they got us together because we were, as a lab, we were looking at the innovating and solving the problems that require training at a scale, distributed training, and solving problems that were difficult to solve at the time. And so we were happy to meet with Dr. Ion Stojka and his team and establish collaboration, work intensively in our own shop, and interacted with Ion and his team, Robert and others, relatively frequently, and we got great support and established great collaboration before, at the time when Ray was, of course, emerging as a framework, and we incorporated it in the research that we're going to present today. And what we're presenting is indeed an experimental framework. It's not intended to be a production framework. It's intended to explore um, important things and to give us the freedom to experiment. And in that context, Ray was an excellent tool or library to use because it allowed us to quickly iterate and develop and implement things that we were interested in implementing. And I will certainly switch the presentation and present the details what it was that we built. It's a work in progress because, as I said, um, you know, it was inspired by important problems. It was inspired by an idea, and at that time, abstract idea of unknown infectious disease happening and us wanting to improve the system for surveillance alerting, real-time decision making. And who would expect that actually in February and March, when we were working on this framework and finishing it up, we got hit by this global catastrophe, and we switched our work to a large degree to actually working on solving the assisting in a COVID response. My lab has a very significant role, national role or international role in the response in terms of using our computing human and physical capabilities. So we have unfortunately not completed all the elements of the framework realm we're going to present today, but it's still work in progress. But we have an important and interesting, I would say it's more interesting things to communicate because importance is a relevant thing. What's important to us computer scientists in these days is not always as important to the society at large. So I will be slightly more cautious about calling things important, but for sure it's interesting, I think. And so I'll talk about it. I'll switch to the presentation and walk you through what we did so far, some of the core ideas that brought us to this kind of development, how did we use Ray, our initial experiences with it, and certainly future work, because we hope that this all will be over. I hope soon. Soon is a relative term, but we would like to come back to development with Ray and to do more with Realm, which is our framework. So I'll go to the presentation now and just tell you what we've done. Thank you. So let's talk about our work now, specifics of what we call real-time analytic monitoring, or REALM. So for the rest of the presentation, really we'll talk about three important components, and that is motivation and background. Why did we engage in this kind of work? Because I think that the story is interesting universally, and I think the problems are important universally. And then we'll talk about the architecture of our implementation, including, I would say, the model protocol, or model updates protocol, and then our uses of Ray and some of the observations. As I said, performance, we really didn't go as far as we wanted to go, given the priorities have shifted in terms of using our computing resources. And then in summary, we'll talk about future work, because there's lots of important future work left that's going to yield some, I suspect, important answers that might ultimately inform the roadmap of the Ray itself. So the motivation for this work is twofold. Um, we were working with our partner agency, specifically Department of Veteran Affairs, on the problems of suicide prevention and development of, or speeding up of, the predictive algorithms. And these models today, and they're state-of-the-art model in the field globally, because unfortunately this problem has been prevalent within these organizations in terms of care for patients. The problem of predicting which patients are at risk of suicide or death of overdose. And of course, these models today are, single model deployed across multiple sites. And at the same time, by working with the colleagues from these organizations, we were inspired by one problem which unfortunately became, in the meantime, overly relevant. And we were unfortunately not able to work on it in a realm fashion. We had to work on the problem by doing classical analysis and supporting the national initiative for understanding and reduction of the understanding the impacts of the COVID. So the two use cases are, as I said, suicide prevention surveillance and overdose prevention surveillance and infectious disease surveillance. Specifically, the motivation came from two case studies or two pieces of statistics, you can say. So first, the rate of suicide, especially among veteran population, is relatively high. These figures are from 2017, I believe. 2020, 2019 figure are that 20 veterans commit suicide a day. Not all of these veterans are seen by the VA system at all. They exist outside of VA completely. They have never sought care within a VA. Yet this is still a pretty high rate, of course, and our goal was always to try to alter this number. Thankfully, there were some very important initiatives within the VA, such as ReachVet and Storm projects, that have already lowered the rates by, I believe, 25 or 30%. But the problem that specifically motivated, I have to say me in this case, because I was probably one of the earliest people on the team working with these great people who are helping solve this problem, is that there's one model deployed across the nation, and then these are rare occurrences, even though it's a high number humanistically, but you do not get anything close to, I don't know, tweets and messages and whatever else is being pushed through social media. You can imagine those rates and the rate of learning you can accomplish in electronic commerce and what Amazon can learn about people's purchasing habits versus what drives the rate of suicide, what risk factors exist. So, you have notes, you have other pieces of evidence, but it's relatively sporadic. And as I said, there's a one comprehensive model deployed across all sites. But what if the new data appears in one site or another? You have, I don't know, physicians seeing patient in Florida or California, and they're learning something new. And not only they're learning something new, and this is something that was really to a large degree motivated for myself reading these examples when for instance, veteran walks out of hospital and commits suicide, is that how do we create a framework to inform physicians who might not be therapists, they may be a primary care physicians who are not as trained, to find ways how to send them alerts and inform them that they should send this particular patient to follow-on care or send them to a therapist or have some, we can say real-time intervention to help them. So the issue was the problem of real-time updates and learning in real time and propagating those updates across the country. And then two, alerting primary care physicians or point of care individuals that they should react immediately, because what frequently happens in the models that we've been working on, and we had some great successes with speeding up some of these algorithms from running in 75 hours to running to 15 minutes and bringing them close to real time in terms of predicting, but it's still predicting in a very much offline mode where you are not in a direct touch with the individual. You're trying to find which individuals are at risk. But what if you have individuals in the clinic? Can we do something then? And can we learn at the same time and then propagate change? So that was a big driver. Second driver is a little bit more, in one way, is a little bit more abstract because we're not working a problem. On the other hand, today it's unfortunately very relevant. And that was the problem of occurrence of the new diseases. Many surveillance models operate on models being updated and pushed out every 24 hours. So if there's new global or national alerts, they get distributed out, but it takes some time. And we want to look into a problem. What happens if the outbreaks happen at multiple places at once and they occur small? Again, you have a low sample and outbreaks grow. Can we learn in real time and update all these models? In this case, I'm presenting these yellow dots. I'm purposefully not using specific example because this is inspired work. This is something we've done for these agencies yet, and so I don't want to create a wrong notion that this is the work we've done for them or this is the real problem they have. The real problem is there, but it's, I think, problem global is how quickly can you update decision-making models and learn from data as the situation unfolds. But it was informed by the case studies that our colleagues who work in infectious diseases inform us about. And again, how can we learn? How can we learn about and correlate events that are happening geographically, they're correlated or geographically dispersed, but similar because of their characteristics in terms of, for instance, presentation of symptoms and so on. And then have an infrastructure to update models across. So learn and update the models. And so to summarize those challenges, and some of them were inspired from a epidemiology or the medical field, and some of them are computer science challenges. So first is learning on low sample data. You start with a model that was trained on very incomplete data, and as the data arrives, this model could be updated. This is a very valuable data that doesn't frequently occur. And then two, how do we build infrastructure to overcome slow updates to distributed models as they exist today? And some of those are infrastructural issues, and some of them maybe we can say bureaucratic, but either way, it would be good to demonstrate that updates can be done in real time. And then, of course, work on a speed of learning propagation as the things get learned. How do we propagate that? And again, we're working on a low sample data, so there's a challenge of when do we know it's good to propagate, and it's important. Of course, there's a whole field of statistics that deals with that. And then finally, collisions and conflicts. What happens if multiple sites are sending parameters, either at the same time or they are reporting the same, performance metrics, but the parameters are different, and how do we resolve these? And these are still largely for us problems that we need to work on. So to address the inspiration first that I mentioned, and then some of the problems, we put together this realm architecture, which I'm going to describe in the following slides, and we'll describe in terms of use of our own object model we put in place, the uses of Ray, and then Ray serve, and then talk about some specific kind of protocols that emerged from doing this work that are also still work in progress because as we are learning more, as I said, Realm is an experimental framework. Its purpose is to simulate situations that we learn from it. And so we are discovering new important questions and trying to address them as we are developing it. I'm not going to spend too much time reading the slides. I'm just going to tell you what this slide says ultimately. Realm is an experimental framework. It really uses simulation of it has a simulation component that simulates events, and it allows us to examine both these problems of learning propagation, but also propagation in terms of distributed processing. It is an event-driven framework for high throughput processing. It's ultimately intended to support at least, if you talk about, let's say, V8, so it is the largest integrated health system in the United States with 1,700 hospitals, and they're emitting new events all the time. And so we want to be able to process them without delay in real time. And then we also support hierarchical inference, and I'll talk about it in more details, what it means. I think it's an interesting problem to discuss. And we use several design patterns, specifically Observer, in terms of creating event registrations and all that. And then we ultimately ended up implementing domain-specific language for network topology and data flow, because we looked into, more we started working on this problem, more we started seeing similarities with networking protocols and distributed databases. And so we implemented a domain-specific language to define the topology of all these processors and the models. So starting going into details of what is it all about, you can imagine on the left that you have electronic health records application deployed across the health system. And it can be a single electronic health record application. It can be a variety, Epic, Cerner, custom ones, whatever, across multiple hospital systems. But let's say they're all conforming to the same event standards, how they're processing certain medical events. And then each electronic health record system has its own local model, which is observing events, acting on them, but as it's learning and observing events, it can make real-time decisions. If it's observing something that is learning new, it can propagate these learning parameters to what we call regional models, which are more specialized models, or hierarchical models that are used to differentiate one region from another, and these regions can be defined either by geographic properties, it can be defined by the properties of the population, it is a little parameterized, and then there's a global model, something we start with. And we have used that in examples of conducting certain statistical inferences, deep learning, and specifically our interest was in the realm of the, no pun intended, natural language processing information extraction. So in terms of distributed models, what they really are a model, some statistical model or some other model that is executing on a data that continuously arrives. The model itself has extra parameters that can be used to evaluate new data, and if these new parameters result, so the model is reevaluated, and if these new parameters or new data results in a different, better performance of the model, then the model can update itself or retrain itself, and it can decide to propagate this new parameter set that it has learned on the ongoing data. So the protocol pretty much looks like the model is operating, executing on a data, triggering particular decisions, reevaluating new data, and updates itself. And if as we said, if the variation observed at this distributed or deployed site is significant, it propagates parameters to the conglomerate of models. And this is where complication starts happening, and there's decisions, and we have support for that, for what I call the regionalized specialization, and that is that you can have a hierarchy of models that can be organized by their specializations, and these specializations can be set up front, or they can be dynamically evolving. If we see that, for instance, based on population, based on the geographic parameters, climate, epidemiological factors, these models self-organize. The way how the parameters are being sent from the sites, and this is where we observe that there's a need to either, based on performance, that we either do a peer-to-peer communication or that we have a centrally coordinated decision between which one to use. So far, based on what we learn, is that peer-to-peer is good for smaller model networks, where the central coordinated is more important for the systems that have a large number of distributed, what we call model states, and the danger or the risk of collision and conflicts is larger. We have seen that state coordinator, that there should be a role for state coordinator. It's a bottleneck. So again, this is one of those things that we keep getting inspired by what we see and what we come up with. And as I mentioned, I'll talk about this later. We're looking into some extended versions of this state coordinator that is either distributed or it has some form of eventual consistency. So the key challenges we observed of what I described so far is that when to regionally specialize and when to propagate. I think it's a bigger question we can answer, but it's an interesting thing in terms of informing a design, allowing for the freedom for some of these deployed models or deployed sites to self-organize into clusters that all share certain parameter sets for their models that are different than the default model which exists in a base state. Two is, as I said, managing distributed parameter state is questions of transactionality and integrity. Very much like a database, when do we do a commit all, or do we allow for some to stay in uncommitted state? Well, how do we resolve that, and how does it impact integrity of the global deployed model? In some instances, these models, it's better to have model period, and it can only get better. And if we don't deploy them all, maybe that's okay. In some instances, it may not be okay, because if we're talking about life and death and suicide prediction, we want to have a transactional deployment of the parameters. And then the question of synchronous and asynchronous propagation. This is very much, almost you can say, inspired from the networking design. So uses of Ray. How do we use Ray? I'll try to go through this quickly. So first, in terms of object model, I'm not going to spend too much time on this because for the sake of time, I'm looking at how much time I have left. Object model of the realm is, there is a processor that contains the overall driver logic. It's really just the executor, larger executor. And then we break up the object structure into, there is a source, which is an abstract source, which in this case can be electronic health record that can register itself with the observer, which exists within the processor. It can unregister itself, it can emit event, and it can act on an event issued by the model, so that whatever holds the model and receives the event can trigger a particular action. That's a big thing. That enables us to push to the physicians actions to say, refer this patient to a psychiatrist, or ask this patient to, pursue a certain type of care. And then beyond that, really, it's just an observer pattern, distributed observer pattern. It allows us, again, to register and unregister sources, and to have models affiliated with it that issue actions to those particular sources. And again, if you go back to the previous slides very briefly, if you look at this, EHRs are sources. The processor coordinates the flow between the events going into the models and how they're propagating further. And in terms of Ray, why did we use Ray? So this goes back to the original story. It's a scalable, easy to use framework. It supports distributed execution. We hopefully all know that it's based on the actors, which is, we have learned for the last 10 years through akka and other, actor-based frameworks, reactive, that it's kind of easy to think about actor-based models. They're not always ideal because they introduce certain overhead through that kind of design, but in these instances, it was really helpful. Supports asynchronous computation, synchronous communication. It has a real simple API. That was probably one of the biggest motivators initially, because when we first learned about Ray, I remember we're sitting at Berkeley with Ion, and he was presenting. We're talking about Ray in context of reinforcement learning. First thing was that attracted us to it was it's Python, sped up by C++, and very easy to start get going. And in the meantime, we found utilities and array serve, so that's how we got to that point. So how did we integrate array serve into Realm? It's a really array serve provides this distributed data flow fabric with HTTP, communication, and gRPC underneath. So really, our whole backend layer between the actors and the communication between the models is all facilitated by arrays gRPC. We did performance evaluation on our system. It worked very well. Performance is great. So we're very happy. Easy to use. Running pretty fast. It allowed us to create this experimental framework and go with it. We did not get chance. This is the part that unfortunately interrupted us in March. We did not get chance to. We set up Google Cloud Cluster for this, or wanted to use it on our supercomputer. We couldn't because we had to redirect all the resources to the COVID-19 response. So this is something that we will have to continue this work. Hopefully, when things get back to normal and good. We wanted to look at, to really conduct a scaling study as a function, in terms of communication, as a function of number of factors involved, numbers and sizes of messages. That's something we'd like to see, how these parameters and what are the trade-offs between. Initially, we were working with a linear regression model just because of simplicity, but now our ambitions are much further in terms of transfer learning that we want to apply, and special learning in the context of transformers and natural language processing. So our initial work was something called Facet, which is this is a long story. I don't have time to go into it now, but originally training on a mimic medical data set, learning new annotations, discovering new clinical terms mentioned in the notes, and so on. So this is something we really wanted to get into, and we did a pretty good amount of work, but it's more to be done. Overall observations on the array architecture, we were fans from day one. Expressive, easy to use, easy to extend in many instances, or actually easy to embed. At that time, what we really saw as a need for enhancements was to allow, if it's possible, subclassing of certain array components to increase ability to do to kind of improve the design composition. Array actors to know its array handle reference. That was very handy because we needed it for handling of our own models that were kind of implemented as actors. And then task ordering, prioritization in terms of resolving the bottlenecks. I'm not sure if that's on the roadmap because, like I said, we existed for the last few months in darkness. Otherwise, we were very frequently talking to Ray team, and now we are just talking to our internal people solving these other medical heart problems. Eduardo had this idea of federated learning, and that is a new library for Ray to support federated training learning. Because what we are doing, in essence, even if it's not in a pure form like you would see a federated learning in a context of distributed deep learning models and parameter servers or distributed parameter exchanges. It's not that far. We didn't go that far, but I think we could, and that might be an interesting addition to the array itself because we already know that RTune and array serve, these are all emerging components, so this might be another one to consider. And of course, ability of local models to interact with composed models like actor groups and so on. In summary, I'll just be very quick on this. What we demonstrate today is an experimental framework to generate ideas, and Ray has been exceptionally good for us in that context because we could move fast, we could do lots of things, and Ray provided plenty of functionality and abstracted us from details that we could do in C++, MPI, some other actor framework, but this was Ray provided us a really great balance of available functionality to a simple API, so we don't need to worry about details, and at the same time having a satisfactory performance for what are we trying to do. Our future work is really going to be focused on performance experiments in full distributed mode because that's the part that we actually want to complete and that's left. And then the second part I think is going to be interesting is this trade-offs on transactionality and consistency. So, there's a lots of work done in databases on this, but this combination of treating parameter distribution as a data distribution problem and its own unique problems that combine performance of the model and the function of these parameters and their ordering and their similarity or identity, that's something to really get into. So I will probably do it in parallel with performance experiments because it requires two different research directions. So with that, I think I'm for sure out of time or right at the end of my time. I will stop. I just want to acknowledge, of course, the Department of Energy and Oak Ridge National Lab managed by UT Patel for being our home where we do this kind of work, and it's fun because we can. I'll stop here and open the floor. I know I have a few minutes